Presenter mode if you use PowerPoint.
Yeah.
And sometimes I see, no, this works. This works.
Wait, I'm not okay. I have to go back like this. Perfect.
Yeah.
Great. Great. Ciao. Yeah. Yeah. Yes, I just connected with the electricity.
Yeah. It's a business that we can do. It depends on your local settings. I give out Yes.
Do you want to disconnect?
Okay if I quickly?
Yes.
I guess so.
I guess. Good. Interrupt sharing. Okay. But sorry, when can we do it? It's my sister. I am at the book now, and I want to take her home. I'm sorry.
Oh, vraiment de Zoom? No, it's
Je suis.
Yeah, I don't know, maybe it depends on the time. Yeah, I would try to make it not in the presentation mode.
Okay, and so yeah.
I would try this for the first session, but
we didn't have the extension to say, but then ourselves, but then
now in Zoom. Right now I can share only screen here. But actually to share, let's share a screen of the slide, right? I can share this. That's a good idea. Share the screen. But now it's like the laser pointer. On the Zoom, are you on? Actually, here I can see the Zoom. Is it? It's fine. It's just the screen.
Okay, so you share the screen, but it's not.
I can try quickly the other one. The other way. Yeah, I'm going to smart.
so
Yeah, then you don't have the green thing. Can you actually find the things? Actually, no, here he has the Zoom open. I think this must be the Zoom link. Right?
It's your.
Yeah, I'm just debugging how to do it properly. So
Okay.
Then it's not clear.
Why is it not clear?
No, I think if you share the window and not the screen, after you open the PowerPoint, this seems to work for me.
Ah, so you have to.
Well, I select my MacBook program and then I do full screen.
Even if they see the presentation.
Yeah.
Indeed, not okay.
You want to share again?
Yes, always better to.
Multitasking.
Okay. Say ciao to Pasquale. Eh? You work with him? Yeah. I'm very friends of, I mean, of Fabrizio Minganti.
Yeah,
Maybe you
sure.
know.
A lot with you. He sadly left.
Yes.
now.
Yes, that is.
Do you know if he's enjoying Paris?
Yes, I know because I work a lot with him and we are friends. And I mean, he really find himself well in Paris, I would say.
Yeah.
Yeah. Okay, so I do sharing, I do this, and then only later I do this, and it seems to work. And then I can. Okay.
Can you get the laser pointer? I guess.
No, yes.
You have your pointer.
No, I don't. This is from. I never get how.
This didn't work for anyone, I think.
Okay, but the important thing is that it works. This kind of. Okay.
I think if you do the laser pointer here, you can also point if you need.
Yeah, but. Too complicated.
What is yeah, they're all. Yeah, I do have sulfur, and then in my but it so I think and you know, but 8 hours and And this but that um, and many now Um. This is just a general. Yeah. 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 And then you go to against. Exactly. And then you. And.
I will share the session.
Thank you. I'm sorry it will be mostly the same as the last talk.
No, but it was a very good talk. Yes.
So do I have to use this? Yes. Yes.
But I can speak up. Welcome everyone. Thank you so much for joining our last session of today. Our next speaker will be Alberto Biella from Dresden. He will be telling us about the quantum signal effect in the universe.
Okay. Good morning, everybody. First of all, let me thank the organizer for setting up such a nice meeting for the organization and everything. And then thank you for all of you. You are really the survivors of the conference. Today, I want to talk, it's a bit strange to give a talk with a microphone, but let's start. So today I want to talk to you about some project that we did recently about understanding the quantum signal effect in many body systems. Okay, so the talk is basically, what does it work? Sorry. It was working.
Maybe you can click on the.
Okay, nice. Okay, the talk is basically bipartite or two-partite if you want. The first part, I get to discuss some concept of the quantum signal effect in bosonic system, and one-dimensional Bose-Alpha lattice in the presence of compatibility. In the second part, some application of the quantum signal effect in quantum circuit, and I want to discuss the protection of in the context of simulation of lattice-rich theories with measurements. And if I have time, as a bonus, I would like to talk about a recent project about connecting topology to the quantum signal effect. So these are the main people involved. On the left side, many thanks to Jeff Mackey, who will move in the next week to COSA, so it's really the engine of our project on bosonic system. And then other people in Trento, including Matteo Pelleraugas and Philip Hauken, the expert on lattice gauge theories. And then if I have time, I want to talk about a recent project that I'm doing with my master students, Severino Zeni and Alessandro here. Let me set the stage. All of this basically, let's say, belongs to our work that is many body open quantum system. But when you know with that, you already saw this concept a lot in this conference, but let me just give my take on this. So I would like to consider a quantum system, generic, that can be atomic, photonic, quantum system, and I want to allow for exchange of energy and particle with something bigger, but they call out thermal bath, for example, or can be a measurement apparatus, or simply the continuum of the electromagnetic field. So this framework has been around since many years. It's enough that you take a textbook of quantum optics if you want to describe the state of a photon in a cavity, you need to describe leakage. But what we are interested in the last decade is the behavior of many particle systems undergoing simultaneously dissipation and internal interaction. So when we want to understand the interplay between these ingredients, so you have to imagine that I have a Newtonian with some internal parameters. Here are G in the sketch. Then I have some sort of dissipation, for example, happening to the environment with a wave gamma, and then maybe I have some gravity. As we saw in this conference, this situation is easily realized in many frameworks, from QED cavities to quantum circuits. So this macro field along the years gave rise to several subfields flourishing. And let's say these are a bit the sketch of what is interesting, in my opinion, in this context. You can, let's say, study, for example, dissipative preparation of linear phases. So how can I use all these ingredient engineered phases that are not possible to be, for example? Then another interesting topic is about dissipative criticality. So what is the nature of criticality of dissipative phase transition in an open quantum system setting? Last but not the least, measurement induced physics. As we saw, there has been a proliferation since 2018 about understanding the interplay between coherent and dynamics and measurement. And in general, it's an interesting setup where you can study complex non-equilibrium physics. Okay, so in this talk, I will talk about something that is a bit overlapping with everything. That is, what is the dynamics of a system that is strongly coupled to an environment. And the environment, as we will see, will set severe constraints to the dynamics. And I want to discuss the emergence of quantum Zinn effect in this context. The first example that I would like to bring to your attention is simply the Boteaton one. So I have a one-dimensional lattice, and I have two energy scales in the program. The first one is the bosonic copy, and the second one you set the scale of the nonlinear. As you know, this system may undergo fermionization. What does it mean? It means that if U, the interaction is very, very large compared to J, the system fermionizes. So double occupation of a given lattice size is forbidden. So we have an energy constraints that constrains the dynamics that do not allow for double occupancy at a given size, but and you can think that it creates fermionic correlations. Okay? We have an exact solution for this problem, a fermion to boson strong interactive boson to free fermion mapping. And what you have to do basically is to do a Jordan-Wigner transformation of your variable, move to the case space, and then your endpoint is the Lagrange and the conservative quantity adjust the population of these fermionic moves. So starting from this, let's try to add another ingredient. So on top of the unitary dynamics, I want to put some incoherent losses. And in particular, the kind of losses that I'm going to consider are two-body losses. So I evaluate on each side pairs of photons. Okay? This is very interesting because it allows us to move from a regime that is the so-called fermionized regime that arises for very large U to a dissipative fermionized regime. Indeed, this kind of losses introduce an additional mechanism that for which the double occupancy of a given site. This phenomenon has been, let's say, proposed in 2009, and that goes under the name of dissipative fermionizer. So you ferminize the system not because of energy, but because of strong two-body particles. So if you want a bit of math, in the regime where gamma velocity is much larger than J, you have a process that basically takes two bosons from two adjacent sides, bring them together proportionally to J, and then very quickly you evacuate them. But if the losses are strong enough, you can eliminate the upper level, and what you are left with is an effective theory for alkyl bosons. Okay? Alkyl boson is really what remains of this gas after long, because they are difficult to evacuate because they don't have other occupancy. So you write an effective long-time effective theory for these degrees of freedom, and what you get is that the problem, the Hamiltonian part is kind of diagonal in these variables, and the losses now happens with this nearest neighbor fashion. What is important is that the coefficient that you find in front of the losses of the double variable is now very different to the one you had before. And this case has 1 over gamma. This is a typical signature of the Zinn effect. Now you probe a lot with gamma. Gamma is the rate, and the effective gamma for the let's say the long time small goes as 1 over gamma. Okay, so a slow dynamic. This is not just theory, but the theory works pretty well with a series of experiments. For example, rubidium molecules in a one-dimensional lattice that has stronger elastic interaction, an interaction that we can tune. And what you can see is that the more the dissipation rate increases, slower is the decay. Okay, and these results are based on the theory I cited before. Okay. Very good. What does this has to do with quantum Zinn effect? As you know, there is a one-to-one correspondence between the Linear equation and the measurement. In particular, you can think that having homogeneous two-body losses in your system correspond to proving the double occupancy of a given lattice site. So you can define the stochastic dynamics defined by this Sparse operator. And upon averaging this stochastic dynamics that is right to trajectory, what you find for the mean state, so the average of the main trajectory, is a linear mass equation. Okay. Going from the right to the left, there is an averaging of a trajectory, so you will information. Of course, let's say, given a linear dynamics, you can invent infinitely many around. So that's why a bit of just this one that to say why in the literature people refer to quantum Zinn effect in very different systems. When I heard about quantum Zinn effect, I always think about monitor system, but this one appears in the literature also in the context of linear dynamics. So why is this interesting, this scenario? Because in the regime of strong dissipation, we have a very interesting effect going on. The first macroscopic effect, you can study the depletion of the population. Okay, you plot n as a function of time. The steady state is going to be triggered in the vacuum, while you can study how we approach the vacuum. In a mean field fashion, what we do is simply provide the equation for the population, and you get something as n dot proportional to n squared. This is for the double two-body loss. But if you play in the fermionizer language and if you plug a Gaussian answer similar to what Diego proposed before, you can put a set of rate equation for the reliability of your model. Okay? Note that if gamma is equal to 0 and dot k is equal to 0, it's simply a Bose-Einstein model in the fermionizer regime, and the population initial node is conserved. Here we allow for some dynamics. Okay, remember, small gamma, the original two-body loss rate is big, while the bigger gamma effective is small because it stays as 1 over gamma. This is the Zinn tensor. If you solve this equation, you find that the decay dynamics in this regime goes as 1 over square root of t. Okay, very different from a figure result. And this is confirmed by full simulation that you can compare with the equation approach up to 16 size. Okay. And also these internal dynamics in the fermionizer regime give rise to a peculiar behavior in a case regarding the occupation of the modes. You can play the same game in a continuous scenario. So you start with the linear model and you put your dissipation in the continuum. And you can define the standard, let's say, Tom's gas by playing with the elastic tapping constant, but again, you can define a dissipation in Tom's gas by playing with the dissipation. Actually, what we found that matters to define some sort of thermoisogen is the linear combination between the elastic or the inelastic and the inelastic scattering effect. So, very good. Again, we can plug a Gaussian answer, this time in the continuum. We get a set again of the equation with a different dispersion relation because now we are in the continuum and we have an effective dissipation. Again, we find that this one of the square root of this of the universal function, no matter if you are in the lattice or in the continuum, but we find a different relaxation in this case that depends on the fact that you are in the function. So, the next step was to try to introduce some spatial homogeneity into the effect of it. What we did basically is to define space-dependent distribution that it tells you the probability to find a fermion with momentum k but in position x. Okay. Within the local density approximation, what we can do is to try to put lossy Boltzmann-like equation. On the left, the first term on the right-hand side is basically the rotation induced by an harmonic confining potential, and the term on the right is the two-body loss. And this is the typical dynamics, so you have rotation and frequency omega and the depletion that take place according with this k minus q rule. So more the two fermions are far apart in momentum space, more they are likely to be dissipated. We can make it more quantitative, and what we found is that basically the presence of the trough set threshold in time, distinguishing between the 1 over square root of t behavior and the mean field 1 over t behavior. So more stronger is the trough, sooner you get the mean field behavior. So very good. All of this is very interesting, and we went on with the characterization of this quantum fluid in presence of two-body losses. And what we did, and maybe here I don't have time to discuss the details, but we characterize what is the nature of the collective mode. You know that if you confine a Bose-Gas and harmonic rock, one of the main features that has to do a lot with interaction is the emergence of collective mode. So you shake a big trap, and you have the breathing at a certain frequency that has to do with the interaction in the system. So we expect that in a system with strong body losses will influence this kind of motion. And what we found, first of all, is that losses basically quenches the system automatically. So usually in this kind of experiment, when you want to excite a reading mode, you need to quench trap. Here you don't need to quench everything, you just study the evolution of the gas. And losses basically puts the system locally in an equilibrium situation, resulting in a consequent redistribution and distribution of the system. So you just, let's say, study the evolution, you prepare your gas, you study the evolution, and what you see are oscillation in the quadrupole mode. Okay, here is a mapping of the distribution function from the momentum and position space to angular coordinates. And what you clearly see is that the dynamics excite some mode with a given frequency. This can be understood by performing a mode expansion of the Boltzmann-like equation, and you see what are the emerging frequency. We characterize them and we discuss the dependence with respect to the intro. So, let's say my point in the first part of the talk is to say that the body losses on top of an already interesting model that is the Bose-Alta system gives rise to qualitative new physics that can be characterized. In this case, within a Gaussian answer, and we have several dynamical properties that depend on the degree of the coupling with your variable. This is, let's say, as I told you, the first part, more fundamental physics thing. So, how we can use measurements and dissipation to use thermodynamic and how this constrains the quantum evolution. This was the general question at the beginning of the talk. In the first part, I show you that we have some interesting but still fundamental physics, not a lot of application. But in the second part, I need to convince you that quantum zero effect can be useful, for example, to protect quantum simulation, protect quantum information. In particular, for this project, I got like a people in Trenton, and we started with one consideration of a lattice gauge theory. We have a sigma and a tau sides. Sigma sides are the charge, tau sides are the field. As you can see, this Hamiltonian, the part proportional to J, allowed to move from this configuration to this configuration, where you basically move the charge and you flip the sign of the magnetic field, of the electric field, and this gives rise to a lot of extensive number of local symmetries, okay? So this means that if you start from a gauge invariant initial state, you are supposed to stay within the set of these local charges for all along the dynamics. Unfortunately, in our implementation of lattice gauge theory, you can have a difference of error that we are summarizing in this error Hamiltonian. For example, here I have an assistant copy of the charge, and I have, let's say, sigma x in the tau x in the magnetic field. This does not commute with the local charges. Okay, so the idea is that the ideal evolution along the green line conserves the charges. Then I have the real evolution that violates local gauge symmetry. And what I want to do with measurement is project that along the ideal evolution. So basically, this is the relation to what the quantum effect is, in the sense that I define a zero substrate. In this case, the zero substrate is going to be defined by the charges, and I want to measure to constrain my dynamics in this useful substrate. So the way we did that is on a circuit. So we have a circuit implementation of this lattice gauge theory. So you see the tau side and the sigma side. The first part is what implements the Hamiltonian evolution, while the second part are measurement. That we go passive error mitigation. I just measure and I control the evolution of the system. I can do more. After I measure, I can do something active and mitigate the error. But I don't want to discuss this layer here. I want to just discuss the taking a lattice gauge theory with error, monitoring the charges, and somewhat making the dynamics better. So, how we did that? Basically, suppose that at the time t, your state is in what they call the physical subspace. So a subspace with well-defined local charge. After time big delta t, I have a probability alpha to stay in the physical subspace, so where the symmetry is conserved, and then I have a probability beta that's where to be in a non-physical subspace, where the symmetries are violated. What I do is simply to see not coupling the theory degrees of freedom with ancillary degrees of freedom, and basically I have some ancillary degrees of freedom that takes value 0 if I stay in the physical subspace, and it takes value 1 if I violate the symmetry. And then I perform measurement on the ancillary degrees of freedom. As a result, at each shorter step, GX1, the value of the charges is improved in the ancillary degrees of freedom. I need an order and a scale, and I can monitor them. I can be a bit more clever and write what is the density of measurement. Density of measurement, I simply take n measurement after n times n step dots on the grid. This is the depth, how many measurements I'm doing with respect to the time evolution. And since I parameterize the big delta t as an n step small delta t, I have this density of measurement. So how discrete, how let's say continuous I'm doing the measurement, more there is a probability to have a measurement. I can find what is the equation for the average dynamics given this Gauss operator, and what I get in the continuous limit, of course, is a linear Maxwell equation, where basically the dissipator, the jump operator, are simply the charges of the lattice gauge theory, and the effective strength of this jump operator is set by 1 over big delta. That is my effective delta. Okay. Let me just say that we are not the first to write this equation, but there was this paper in 2014 proposing indeed to protect let's say against error quantum simulation of lattice gauge theory, inputting classical noise on the charges, and if you input classical noise on the charges and do average, you get exactly the same equation. Here we obtain this average equation because of measurement. What is interesting is what happens if you study the spectrum of this linear master equation in one aspect gives you a feeling of what is the asymptotic decay rate of the problem. Here I'm plotting the real part of the eigenvalue, that is what is the decay, as a function of small gamma, that is the density, the measurement square, over delta, which is the square of the error. For small gamma over delta, as you can see, there is a pretty monotonic behavior. So all the states basically acquire alignment. So there is nothing interesting going on. After, I would say, a critical value of gamma, I'm not saying critical because it's a exact generalization for phase size. You get that a new state branches out and progressively becomes dark. And it's easy to understand that these dark states are going to be closer to the symmetrical technical states, in the sense that if I take gamma and I put it to infinite, the dark state now is the measurement rate, the dark state of the jump operator of the Limbadia are the states that concern the local charge. So we have in the, let's say, in the stronger gamma limit, a well-defined subspace of states that are the good states where I want to perform my simulation, that are somewhat decoupled for the with respect to the rest of the dynamic. You can really, let's say, try to plot some quantity of interest. Here is, for example, the density of size, and this is the exact simulation in a given regime. I put some error in it, and you can say there is some scrambling of the dynamics, but then I can correct back in the zero regime by post-selecting on the trajectory that are projected in this subspace. And in this subspace, the dynamics is very similar to it. If you don't do this, or if you want, if you increase the strength of the error, you enter a normal regime where you have just a lot of scrambling of the information. You can never cover the exact, the ideal path of the simulation. What is interesting about our protocol is that we have a parameter that allows us to reach the continuous limit with the density of measurement. So I'm not discussing this plot, but what I can say is that we compared what is the fate of error collection in the continuum limit or in the discrete limit. The two approaches give rise to the same value, so the average dynamic is the same, but the statistics of the trajectory is different. So, for example, if you plotted the violation of the, let's say, of the local violation of the symmetry, you find the statistics with the same averages, but with different probability distribution. So, let's say one can play with the torture evolution or continuum evolution according to what one is interested in. So, yes, with this I conclude the second part, but it was more applicative and it was about error correction. How many time do I have? 5 minutes, perfect. So in this 5 minutes, I want to measure, let's say, the last thing that we are doing to try to understand better the onset of quantum field effect in many body systems. What I mean, what is many body is a, let's say, it's a difficult word. So we start with 2 body. And in particular, I want you to consider this scenario where I take just a qubit that undergoes 2 different kinds of measurement. Each qubit is monitored. Operation of each qubit is monitored with a rate gamma 1 that is equal for the left and the right qubit. And the 2 qubits undergoes radio oscillation at a frequency omega s. If I look at just one of the 2 qubits, the quantum field effect is well understood by studying the ratio between gamma 1 and omega s. If gamma 1 is larger than omega s, I cannot perform full rotation in the block sphere, but I have a constrained dynamics in just enough part of the blocks. What we did is to introduce an additional ingredient that is to couple these 2 qubits with another kind of measurement. So not with physical dynamics, but with a measurement operator that couples the density of the qubit. So mathematically, what I had is a stochastic evolution where the first part is the unitary rotation and the second part are measurement. I have 3 different kinds of measurements. So I have M1, the density on the left, M2, the density on the right, and M3, the correlated density. This can be done by playing with properly design ancillary degrees of freedom. And then, of course, if nothing clicks, I have the no-click evolution that is ruled by this M0 outcome. The problem is difficult enough because already
featuring the linear space of two grids is just too big. You cannot really visualize it. So since we wanted to get a really understanding of what is the region of linear space that is populated by the stochastic dynamics, we perform an approximation. The approximation is the Kutzwiller answer. Kutzwiller answer simply tell you that at every time the wave function is factorizing between the left and right. And since because of the symmetry of the problem, each wave function can be represented by a single angle, I have that my litmus case is just let's say the tensor product of two angles. So if I tell you what is the left and the right, you can locate your state in the inverse space within this approximation. It's bad if you want to study quantum correlation, you're using all the quantum correlation of your problem, but you want to capture classical correlation of your problem. And indeed, as I told you, the interspace probability distribution is given by these two angles, theta left and theta right. And what I want to study to locate my state within the inverse space is the probability distribution of being in theta left and theta right. That is just the product of the two data. So understand it is kind of a classical, in this sense, correlation factor. What we did is to study a sort of phase diagram of this model as a function of the two kind of measurements. So on the left axis, you have lambda one that is simply proportional to gamma one. So you increase the local measurement with respect to unified evolution. If you go to the right one, you increase lambda two that is simply the correlated candidate. And what we found by studying the property of this distribution function are three completely different regimes. For example, let's take the regime of one, that is the black dot, no zero effect, normal regime. So you can find the state of your system everywhere. Okay, so the inverse space is completely complete. I don't have any kind of thing. Let me jump to the regime 3 because it's more easy to understand. The regime 3 arises whenever you measure a lot locally. And when you measure a lot locally, you are basically constrained to map the system on a curve. You are constrained on a patch on this soil. You cannot leave this manifold. Okay, so there are certain values of theta left and theta right that you just cannot you cannot explore. The novel regime that we identified is the blue triangle that takes place when the correlated measurements are very large. That is basically locally, I can explore all the theta left and all the theta right, but there are certain correlated combination of theta left and theta right that are not possible to explore. And as you can see, if you map this probability distribution on a curve, they are just too many that are topological distributed, so you cannot flow adiabatically from one to the other. And what is interesting is that we studied also the non-linear limit of this model, and what we found is that there is a one-to-one correspondence that maps the structure of this probability distribution, the topology of this function, to the topology of the flow of this non-emission window. And this, let's say, it's a kind of a recent concept, as far as I know, that is been explored in the group of coders, like Greta, for example, talking about the topological classification of variant distributions. So these are the topology of topography. So it's like the feature that these flow diagrams have. For example, in the first region, I will not have any fixed point of the dynamics. In the region 3, the one on the right, I have a maxima, the red dot, and a minima that works as a tractor. While in the new middle region we found, we have a maxima and we have a saddle point. And there is no continuous way to go from one to the other. But let's say this is a very, let's say, preliminary result, working progress, and we are trying to understand what are the connection between measurements, non-emission Newtonian topology, and this zero transition. Of course, we did the analysis for 2 qubits. It would be nice to extend it for many qubits. It's possible. Actually, we have to find a meaningful way to represent, let's say, the population of your hyperspace to characterize the non-emission flow. With this, I think I can conclude, and I thank you for your attention.
So we have time for 2 questions.
So question about the second part of your talk, where you were essentially implementing a Laplace equation with cross operators that correspond to the Gauss's law operator. So you showed like this plot where on the x-axis you had the dissipation strength gamma versus lambda.
Yes.
And then you argue that you need basically strong measurement rates in order to this error correction scheme to work. Is there actually a critical point, like a phase transition, like in this error correction?
Yeah, that's a-
case where you actually go from, fully working error correction in the combinatoric limit to not working at all.
Yeah, that's a good question. We claim this to be a different system because the only way we have to do is to perform a simulation of larger system size and to
In fact, not because of that.
Okay, yeah, yes, why not? There is no, as you can see, no, the dark states appear asymptotically. So it's not that immediately you are on the right of the threshold, you get a proper dark state of the model, but what you can do is some extrapolation in the sense that what I can tell you is that immediately on the right, the scaling of the error is 1/gamma, while on the left is gamma. So the scale, if you want to extrapolate the result, this is a parabolic scale. In this sense, this is a transition between two completely different versions. But let's say the fully protected, if you want, it's extremely on the right and or extremely on the left.
And where would you say that the critical value would be in this case?
No, we just found numerically that we just found numerically that when gamma is equal to lambda, segregation or non-segregation happen, yeah.
Are there any more questions?
Just very quickly, a lot of interesting slides actually, where they sit on the rank of the reference to this technique where it's,
No, you missed it. No, sorry, we don't have that. It's a very, yes, the physics of my master's student. And yes, we are just working. Yeah, I mean, the main idea with this, for me at least, was to try to have some sort of visualization of all the constraint dynamics. And if you think it's a bit crazy because with a simple qubit, you can really visualize how the distribution swings, how there are regions that are not allowed and regions that are allowed. In a multidimensional setting, we know that measurement will confine the dynamics, but people try to characterize the correlation function, etc., to give, let's say, more a visual contribution, try to characterize the structure of this manifold with, let's say, multidimensional. This was a bit motivation.
Sort of technical question about the error correction.
Yeah.
So you mostly focused on measurement-based error correction, and then you discussed us by taking the further step to diminishing it, and you go into the limit.
Yeah.
So is anything to do with autonomous error correction in any way, where you are somehow just engineering the reservoir? And then on average, you are stabilizing the goals.
Okay, I don't know anything about autonomous collection, so I cannot answer, but I'm happy to discuss it. I don't know, honestly.
Then let's speak again. So our next speaker will not be Paola Tapinos, in the program. Leo. To pronounce your